This is the last session today, and this session we have one paper by Marija Ilic, and I think Marija doesn't need no introduction. Everyone knows Marija; she's been everywhere.
Thank you.
So with momentous contributions to power system research, and here is her paper.
Thank you very much. Thank you for staying. I know there is jet lag for me also, so I'm not responsible for my actions, but I will try. Okay. So the title of the talk, something we coined this term DyMonDS, Dynamic Monitoring Decision System, about like 10 years ago at CMU, and then when I got back to MIT, we kept it. And so I want to explain how we envision this framework for end-to-end management of energy systems and alignment with technical and economic signals and so forth. So, does anybody recognize this picture? So, it's basically what have we been solving the last 2 days and for the rest of this week. We want to basically make the most out of natural resources for very different characteristics of different users. So this sketch comes from the science paper by Elinor Ostrom on generalized framework for sustainable social ecological systems, she called them SES. And she worked a lot in water systems, and I strongly recommend that paper. She was the first woman Nobel Prize winner in economics. And basically the basic idea behind, she went up against the mainstream where she said you can manage tragedy of the commons very different ways than it's manageable and can be managed. And she had these examples like in a Nepal village, people manage their own water usage and so forth. So basically I like this figure because it tells us what's going on. We do different algorithms, different information exchanges and so forth, but this tells me what the big picture is about social ecological system. I have users, I have groups of users, resources, portfolio of resources, and users who exist in some governance system. And there is a table in that paper which basically says that there are some inherent characteristics of these participants in the social ecological systems, which her premise was you can look at their characteristics and say how sustainable the system would be. There was no math or anything, right? The thing that I took out of it was that these interactions. In other words, if you think about this as energy system or electric energy systems, we have supply and demand, but interactions are implemented using physical transmission system, distribution systems, and they can be smart, less smart, and so forth. So I've been doing a lot of work with different students over the last 10 years at least on modeling these interactions between different parts of the energy system. And so the interactions can be IT enabled, but they can carry the information about physical, technical signals or economic signals. And so this is the problem that I'm saying that this is the problem we want to solve. We want to, depending on what characteristics, as it was talked before, if you have hydro in Brazil, the properties of resources are different, properties of the users are different, but there should be some common principle based on which we now design enablers of most sustainable transmission delivery system. And I will talk quite a bit about these interactions. So, as you get older, you get a little bit more pessimistic. I heard Janusz yesterday. So, should we be worried? As I was listening the last 2 days, and I'm sure it's going to be the same way, we are really overwhelmed by this complexity, mathematical complexity, type of things that we have. And it is fair to say that for electric power systems, they were not designed that way. Control and planning was not designed for any guaranteed performance. Now you put these new technologies on the system, you want to operate them differently, and system operators say, can you guarantee the performance? Well, you can't, because from the beginning the system was not designed that way. And that has all sorts of implications that I don't want to go over here, right? There are a lot of people in the US at least working on what they call these interoperability standards, so that manufacturers, vendors of different technologies can exchange information. ABB Gadget can talk to Siemens Gadget and so forth. But what I've observed is that that's not sufficient. What information you exchange, you're using for feedback, for feed-forward, the system is going to do different things. So there are all sorts of implications here, and not to neglect the fact that we have to also rethink teaching of these systems, right? It's multidisciplinary and so forth. So these are the worries that I want to somehow address, and the question is, the premise that I want to put forward is that operation and planning is really no longer just centralized. We have to think about that as data-enabled interactive decision-making by multiple heterogeneous decision makers. You have tons of different users, tons of different resources, small, large, and so forth. So what are the fundamental issues with modeling, simulations, and computations for these systems? You know, we don't know how to stand in front of the classroom and introduce this in a simple way without requiring people to know, to be specialists and so forth. So this dynamic monitoring decision system framework that we're working on is basically one way of conceptualizing what's happening in the system, modeling these interactions and utilizing them for both operating the system, planning, and also for aligning it with markets if the market is, if the governance system is market. So sort of we've been using it to even assess, depending on what functionality you want to give to different components and what is the benefit that component is bringing, to actually rethink even the market design, because markets have emerged first for energy, and so, but there are many other things that we have to think about if you want to align the economic value with the technical thing. Okay, so to start with, why we took this step back to rethink modeling and simulation tools. Again, I don't want to go through these here, some of you know, but if you look at the typical simulation and modeling tools that people use for different purposes in power systems, they are fundamentally weak when it comes to challenges to applying them to the changing systems, because if you want to simulate them as a single flat entity, monopolistic entity, nobody can do that. And I'll show you, like, you can have power plant, nuclear plant has 100 states, hydro plant has 50, and so forth, and they're interconnected with the grid. So if you want to model it as one single thing, I mean, you can brute force the simulations, but you can get some numbers, you can get some plots, but there is very little insight of what all this means. So, and the one that I'm particularly interested in, because I'm sort of like to put myself into control box, control design, is that most of the models that we have in power systems, they are like transient stability model is set of differential algebraic equations. And if you think about what we know about control design for DAEs, we know nothing. You cannot, I think Dave is sitting there, I think he early on did work on that, and maybe he could disagree with me, but it's very hard to, yeah, it's very hard to design control for the system operating over very large deviations in face of very large deviations, here probable performance, if your model is DAE model. But if you think about this, and that's one thing that this dynamic DyMonDS thing helps with, why do we have a DAE model? We have a DAE model because we model dynamics of supply and maybe even demand. We assume it's instantaneous, right? So we have these algebraic constraints. We assume that the transmission system is instantaneous. Therefore, it's an algebraic constraint. And the only dynamics that you have is in the nodes, at best. And so, is that really so when you start now controlling the transmission wire, which has its own time constant, and you can control it and so forth. So this is what we have, and I don't have much time to go through it, but for example, I hear quite a bit, like people in Europe are using Modelica to simulate DAEs and so forth for power systems. It's multi-physics, it's nice, but it's hard to initialize. You have algebraic loops. These DAEs are just not good when it comes to dynamics. And the other thing is, so we basically need to rethink even modeling and simulation of new phenomena. What do I mean by this? Transient stability analysis programs that people run offline for the worst contingency to see if the system is going to be stable, they are basically, they only model, they only model the electromechanical phenomena, a little bit of the dynamics of that you have on electromagnetics inside the machines, but they don't model at all the power electronics and solar processes and so forth. So what one of the students showed here, if you, for example, want to simulate response to study offline if your system is going to be stable or not, using typical transient stability analysis software, you're going to see that the system is stable at the time scale that it captures, right? Now, actually, if you model the dynamics of which comes from the time constants that you have inside inverters and so forth, you see that things blow up at the faster time scale. So we see this just as an example in ERCOT. They have this is a very real problem. They have, what they call it, a control-induced subsynchronous resonance, but it's not mechanical one, it's magnetic one, in which the controlled wind power plant by one manufacturer, power electronically controlled wind power plant, tries to send power on the weak line, which is controlled by, which has a series capacitor controlled by power electronics by another vendor, and these controllers start fighting at the time scale that we didn't even model in our transient stability analysis. Is getting to be very big problem when you have a lot of power electronics on the system. The reason that this was interesting to us, because we were working on better controllers than PID controllers. So if we simulate it with our model looks unstable, TSA tells you it's stable, but our objective was, this is what the student was doing. He was trying to argue that to suppress those control-induced instabilities, he can have nonlinear controllers which will stabilize this thing. And you just don't even see it with simulations. Okay, so we need to rethink the modeling and simulation, new physical phenomena, in particular because at the edge you have a lot of power electronic stuff. The other thing is, I just want to mention this because as we were working with NIST, it was like 5 years ago or so, they wanted to do this transactive energy management. So you want to simulate how the beads interact with the system. If you schedule something, is it going to be stable? Well, if you just model using real power phenomena, even static, you're going to see everything is fine. Now, if the power factor of some loads is not good, you start seeing instabilities in reactive power. And these are quasi-static instabilities. So the other thing, so it's basically the problem on the markets. You need these details, but then you'll get lost in details, and that's what I want to talk about, how we deal with it. So the question is what level of granularity we need to capture what's happening on the interactions with markets, because it's not just energy. And the other thing, people already talked about this at the meeting here, that not all components, not all resources are capable of responding at the same rate. So you need models that capture that. Most of the models that we have for DCOPF, for energy-based clearing, doesn't account for the model which which would capture rate of change at which these outputs change. Okay, so this just as a motivation for what I refer to as maybe some basic modeling principles for simulations. We are using it for this SAP scalable electric power system simulator we've been developing for now a long time. But the challenge at the end is to have very detailed physics model at the component level, and then at the higher level not require much of detail to capture the interactions. And that's, as I described, this is going to be this new feature of power system modeling that enables one to, in multiple layers, capture different level of temporal and spatial granularity. And this also has implications on software and numerical methods that we use. Okay, so this became our sort of staple picture in which the idea is all that we talked about these last 2 days actually can be put in this picture. We call them diamonds. These are distributed decision makers. The talk by Claudia from Brazil was all about that. If I am here, hydro, or what intelligence do I have to embed to capture my own constraints if I'm demand or hydro? And how do I do bidding if I'm in the market? What information do I need to exchange with the control center? So what we have now, at least in the US, I think it's most of the world, is that information goes from the central control center down to distribution level, and there is not much information. So you actually cannot capture, even if you want to aggregate, there is no IT support or SCADA to capture the effect of these responses of players at the agents at the edge, so that you do something more efficient at the centralized level. So the idea is different, and it becomes very big job. For example, John Donady did diamonds just for vehicles and fleet of vehicles. You know, you have to model, you have to decide, they have to learn. The same way it was presented for some other technologies just before the break. And then at the substation level, maybe you're an aggregator, you need intelligence. And so this is, we believe, that the basic architecture, information exchange architecture that one would need. And there is a trade-off between how much intelligence you embed into different layers and what information you need to exchange, at what rate, and so forth, but at least gives you a framework to think about the problem. So I hate to even admit how long I spent on asking the question and driving my students crazy about what is the minimal information that you have to capture without worrying about what's inside. And that's what I want to run us through. So, but the basic idea is that you have, this is what industry is now. You have multi-layered, modular interactive environment, and you need a framework for modeling, for control exchange, and so forth. We did some time ago this edited book on Azur's islands. It was self-contained island, and you show, if you embed this intelligence into demand, this into geothermal, hydro, that you can actually get rid of that ugly fossil power plant in the middle of the island, and the thing with some intelligent control still works. No frequency problems, nothing. So some people have used this as text to introduce the smart grid, because it's sort of self-contained on an island. So what is the basic question that we have to deal with? As I mentioned, the big problem is how do you develop these distributed algorithms given the very unique features of different technologies, preferences, risk preferences, environmental things, and these distributed algorithms, this is the basic idea, would internalize heterogeneous physics, multi-temporal decisions, and uncertainties. In other words, all the complexities are embedded in, internalized into bidding, if you want to think about the market, and then you have relatively simple information exchange in between. And So that leads us to the basic question: does this make sense, theoretically, and can you say something about whether such paradigm works or not? So another way to ask it: can one manage complexity using common protocols for the general case of nonlinear mesh selective power networks? It's very hard, loaded question where you have many heterogeneous dynamic decisions, multiple time scales, different things, right? And so this is work with Rupamati Jadivada, joint work. We have been working on this unifying energy-based modeling of dynamics to manage that complexity. So I'll show you the fundamental mathematical approach to the modeling, and we can go back to, okay, so here we go to the math. We've already had this, like yesterday, Professor Motter was talking about dynamics when you have bifurcations and so forth, but that nonlinear dynamics happens because at the component level you have dynamics which depends on its own states, its own local control, local disturbances, and these are effects of the rest of the system to which you are connected. And so you have just a sort of systems modeling that we use for dynamical systems. And one thing, it's a structural thing in power systems that you can show, doesn't matter what type of technology you have, what type of box you have, that this interaction can always be taught in terms of instantaneous power. That's the exchange. Everything else is internal state. And I don't have time to go through. And these yi's, these outputs at the local level of the component that component cares about, like quality of service, frequency, voltage, and so forth, but local. And this structure begins to help us now answer this question about minimal information exchange. Okay, so let me jump over this because I want to explain it, and it didn't have a picture. So I can think about every box here that it has own dynamics, and there is a lot of work, for example, on bond graphs, about static bond graphs and so forth, where it doesn't matter if this is mechanical, fluid, energy conversion, electrical. You can think that the ports, you can characterize the ports with two variables, which is effort and flow, right? So in electrical, it becomes voltage and current. In fluid, it becomes mass rate and pressure and so forth. So it's very general for multi-physical things. And so these port states and port inputs become very important. So I don't have to, in the interactions, I don't have interfaces, I don't have to worry about what's inside if I just want to capture the interactions, but I need to say something about how these port variables change, right? And they are not just electrical, they can be anything, okay? And so the minimal information basically needed in each module, this is the minimal information. Modelica, for example, is based on the same thing, because at each module you have to have Kirchhoff's law at interface. Okay, so what is the basic idea? Now the basic premise is that we are talking about energy systems. We are not talking about information processing systems. So what we want to know is that as these generators and solar and so forth produce some power, we want to know the dynamics of the work, the energy flow, and the rate of change of power exchange rather than just necessarily some current and voltage, because that doesn't tell us much. So this begins to make the case for mapping that very complex dynamical model, which is technology specific for a component of interest, into something that you can characterize on the interface. And this becomes very important because it used to be that you can model dynamics of large power plants in terms of inertia. Now on the inverters, solar, you have the notions of synthetic inertia. We talked about this morning. It's a sort of an artificial proxy for the dynamics that you have internally in the inverters. But what we see is that these heterogeneous end-to-end conversion processes, this is one conversion process, another one, and so forth, they are based, if they are inertia based, then we have the approximations. If you look at the state of art, for example, in particular for inverter-based control, people start with the droop characteristic. That's a proxy. That's not the right model. With that model, you cannot capture that instability I was talking about in ERCOT. So what we propose is to go on the interface from these port variables, which are effort and flow, to think about energy, dynamics of energy that gets exchanged between different components as a state variable. And then we also know that on the interfaces, we model everything as dynamics, as I said. You don't assume that wire is instantaneous. At each of these memory-less interfaces, you have to have power to balance, first thermodynamics law. Because of that, now you already have energy as a state variable on the interface, power as an interface variable. And I think this is quite important, because if you want to somehow balance very slow varying demand with very fast varying source, you have to somehow in your model capture the rate of change of power. Okay, so this looks complicated, it looks radical, but if you think about the markets, in the markets you have these bids for energy and power. So the only one that's missing is this one. And just this is for EE people who care about the fine difference between rate of change of instantaneous power versus rate of change of reactive power. I'll give you the generalized definition. Those two are the same when voltage doesn't change. Okay, so it depends on which assumptions you make, but there is a case to be made for capturing rate of change of power, but I'll show you that it's really not rate of change of real power, but reactive power that matters on the interface. And I want to argue that you can say something about stability of the interconnected system, about efficiency, formulation, optimization, and interconnected system if you start thinking in terms of these variables. So basically, to summarize, every box, every component, doesn't matter what it is, it has its local primary control, it has its own dynamics, local disturbances and inputs. And for interface purposes, for modeling interactions, we now map this original state space into stored energy, rate of change of stored energy, which is power, and rate of change of reactive power. And I'll give you definitions. Once you do that, here are the more formal definitions. Instantaneous power is basically scalar product of effort and flow, doesn't matter what physical thing. And reactive power is a little bit more complicated. John Wyatt and I wrote a paper in the 90s that I didn't think it would be used for anything. But so you can have notion of the instantaneous reactive power, which is effort times rate of change of flow minus flow times rate of change of effort. This is instantaneous, it's not average. It doesn't have to be for periodic signals. So it took a while to do, but basically when we arrived at this is the following. That internally, at the component level, you have this structure. And you remember I mentioned this instantaneous power is always there, that it goes out. Internally, we have the mapping from many, many complex states into stored energy, rate of change of stored energy as state variables. And there is a relationship between those and instantaneous power and instantaneous rate of change of reactive power that goes to some other components. So this was, I think that this became a golden formula that I want to highlight to you. So this is fairly straightforward. The rate of change of stored energy is power that goes out minus thermal local losses, right? That is first law of thermodynamics. The second law, and there are connections with second law of thermodynamics, this is second derivative of stored energy is, this is ETI is energy stored in tangent space. If you want to look into a lot of mathematical treatment for that, Jean-Jacques Soultin, who teaches nonlinear control at MIT, he does all his proofs on Lyapunov stability for nonlinear systems using energy in tangent space as a Lyapunov function. So this second derivative of stored energy, it's physically very intuitive, is proportional, it depends on this energy that's stored in tangent space minus rate of change of reactive power. This took some doing, the student did that, and I think that was a sort of turning point which helped us. She has the proof that there exists a diffeomorphism. If you are not in energy space, you have effort and flow. That now maps into stored energy and rate of change of reactive power, and they are diffeomorphic. And there are papers that I listed here. So basically, you can go back and forth inside the box between the energy space, the power space that you need for interfaces, and the physics that's taking place internally. And we call these Z interaction variables stored energy and rate of change of stored energy. And the proofs are obtainable just using generalized Lagrange theorem. Okay, so I'm not going to go to the proof here. I want to show you how is this now used. So now I want to interconnect two components. I can have source and load, and each one has the same structure. You know, I can have induction motor, which is controlled, is not controlled, it has this structure. The synchronous machine or inverter-based control of the solar has the same structure. So it becomes very, very simple in terms of interconnecting them. And on the interfaces, we basically have these generalized Lagrange theorem, things that power, the actual instantaneous power that goes out of one box is the same as the one that comes to the, from the other box. And rate of change of instantaneous power that comes from this box is the same as rate of change of instantaneous power that goes out from the other box. We didn't write this, like when we write quasi-static equations for reactive power balance, we don't write the dynamics. And when you start talking about electromagnetic phenomena with power electronics, you really have to take these dynamics into consideration. Okay, some very simple examples. So if you have this RLC circuit, you have a stored, it's very easy to build this model. You have magnetic stored energy in the inductor, stored energy in the capacitor. This magnetic energy in the tangent space for the inductor, you see what I'm saying? 1/2 L instead of I square is DIL dt, and similar for capacitor. And now we have for the entire box, if I want to think about it as the whole box, rate of change, second derivative of stored energy is this energy in tangent space minus what I lose in reactive power. Okay, and there is the thing that caught us by surprise, we were doing first with electrical, but there is complete analogy for mechanical, and we are using this now and working with NASA, with airspace people. Like if you want, for example, to control instability in the engine of the aircraft, you can control it with battery, with hybridization, by controlling mechanical torque twist, which is just that reactive power. So you stabilize that, and so we have a couple of patents on that recently. But the idea is very simple, that you can write this for, doesn't matter what physical system, electrical, mechanical, and then connect them. Okay, so why we were so excited about this? Why have P and Q been chosen as the interface variables? Completely different twist to this is that P actually tells you intuitively what is useful work done, and Q dot, what is the wasted work, at whatever time scale you want to think about it. And both of them obey conservation laws at the interfaces. So that was not all. Now you say, okay, I interconnect these things, I have dynamics of the interfaces. David, you worked long ago with Moylan on stability of passivity thing. So here, you can use similar things for this interconnected system, but you have to be very careful with choosing the storage Lyapunov function to be integral of this real work done, and supply function being rate of change of reactive power. And then you prove, then you begin, doesn't matter what's in the boxes, you begin to establish stability condition in terms of these interface variables, both for the component or subsystems, groups of components, and it's additive, which is very interesting. And stability condition, here one version of stability condition is very intuitive. If I have this component and rate of change of real power, instantaneous power that I push in, should be smaller than rate of change of dissipation, so I'm stable. So the math comes very nicely together with the physics, which we have in the passivity theory and Williams' work and so forth. It's very hard to do it, in particular if you go beyond just the real power dynamics. So this condition can be used for control design to ensure feasible and stable equilibrium, either at the component level, or you can do very similar conditions, because these conditions are additive for subsystem, right? And so you have the sum of all the power injected into subsystem has to be smaller than a sum of power dissipated inside the subsystem. Doesn't matter how many components you have. I don't have time to talk about this, but it's still work in progress, and it's very intriguing, because if you have, I don't have the whole picture, so if you have our typical voltage collapse problem, say I have a source and I have a constant load, PQ load, and the question is, where is that I have a voltage collapse? Where is the sort of fundamental limit to how much the transmission line can transfer? So we've tackled, community has tackled this problem many different ways, but one way to think in terms of energy is that this is sufficient condition. The maximum real power deliverable to load, now you think about load as a component, with constant real and reactive power requirement, which is a tough requirement. This is the most you can deliver without going unstable, and it is quantifiable in terms of rate of change of reactive power of the load times the time constant of the transmission line. And so you can take different systems now and establish sufficient conditions for the interconnections for stability. And we simulated the response when, for example, when you put load which is below or above this maximum, and you can see, for example, that angular frequency goes unstable if you go above that. It's still sufficient condition, but even simulations confirm that. Okay, so that's one thing to take. If you are in this domain where you have on the interfaces state variables which are real power and rate of change of reactive power, you can say something about stability of the interconnected system in terms of just those variables. You don't have to worry about what's inside of what type of technology you have. The other part is when we want to connect the role of reactive power with efficiency because of the markets. Here is a simple experiment. I have a source with some inductive resistive line there, and this is the load. I want this source to deliver maximum power to resistive load, because that's work, right? And I want to vary, we do this in power systems all the time. I want to vary this capacitor so that I reach the maximum. So if you change the capacitor and do the experiment, you see that work done, this is this blue line, increases as reactive power decreases. So basically, The higher the instantaneous reactive power, the lower is the efficiency of the component. It tells you quite a bit, and we actually have to connect it somehow also with efficiency in the markets for those purposes. This is, I don't think it's necessary to go over that. This table is just to show that you don't have to talk about electrical components. It's a sort of generalizable to any physical systems. Okay. So now I want to return to the market. We have the model. I can say something about stability. So the question is, does this help me, to forget about what's happening in the boxes and then sort of doing multi-layered design? So what we have, typically, this is what I think Schmor said he hated this morning, transactive energy management. So you have basically load serving entity and a lot of the load forecaster going to ISO, but there are a lot of agents which are bidding, right? And the question is, can you show how to design the bids by these different agents which have physics, which can go unstable, which we can be efficient or less efficient? Think about them as the boxes that I described. And they create the bids, and the ISO clears the market, these interfaces in the energy space. So typical thing that you are going to get if you write the dynamics of your component and you want to do some objective function, maximize local profit or something like that, given the expected locational price, for example, you are going to get time varying bids. Just if you exchange the locational price and you take into consideration, like it was described by Claudia just before me, you can take into consideration many specifics of your preferences and so forth when you create the bid. So that's all internalized and intertemporal at the bid level. Okay. I just wrote this paper, is under review, but if people want it, I can share. So how do I now, on the simplest case, if I have source and load, and I want to do the optimization for the market, we argued, first of all, that if I just want to optimize physical efficiency, I don't even have bids. The objective should be to minimize total sum of reactive power in different components, subject to all these constraints in energy space, because they're all on the interfaces. But probably this one is most interesting and most unique. I can actually do these formulate this centralized optimization, taking into consideration stability condition. People don't do that. You get optimal thing which blows up, as I showed you before. So the constraints are all in this space. Rate of change of stored energy is PL, and so forth. PL dot is all that we described before. So here is where you pay the price. The price gets paid at the component level, but you have a lot of choice. This is what we want to actually enable. If you have, let's say, synchronous machine, the control is valve position and field excitation, so limits on how much control you have. You know what local quality of service you want, like voltage and frequency, and this is your own dynamics. So basically everything else is in the energy space, but here, I'll walk to the next step. The source standalone component dynamics are messy. So that's where you put all of the complexity. And so one big point, and I think it's a sort of point of departure if we think about this even for markets, because if you do this optimization in energy space, this is a linear optimization problem. You are out of big trouble because we do ACLPF and stuff like that. We don't know where we are going and so forth. And well, it's never free. And the thing that I want to point out here is that if you begin to think about how that market, transactive energy market or market in general, works, from the coordinator level, you exchange expected prices, and the generator level problem is to minimize its own cost subject to physical control design. So these all stay stable and you are within the limits. So you have full freedom there to design the bid function, and you just tell the coordinator up what is the power, what is the limit on power, and the range of rate of change of power, rate of change of reactive power that you can provide to the market, and at what price out of this distributed optimization. So this needs more work. Here we still have, it was first, you remember, this is physical inefficiency, and you always have the trade-off between physical inefficiency and market inefficiency because people give different. These are the bid functions for now for real power by the source, by the load, everybody can bid, and the cost of bids of reactive power now. So we have to extend somehow in the markets to bring the reactive power, but without too much complexity. And all these guys do that in their own little computers, in their little decision makers. They create these bids, but optimization, if the information is exchanged in terms of this energy space, then optimization, you can break it into primal dual or primal. It's basically the optimization at a centralized level is linear. And there are all sorts of other things going on. So this is, you can think about that here. You can include a lot of temporal uncertainty. If you're a battery, you can optimize over the entire day and bid just for 1 hour ahead. But you continue optimizing in a model predictive way, knowing your physics and everything. And so it goes, right? So we have a couple of examples here. I'm almost done. For example, this interaction model, we just started making them, of closed loop solar. So this is what the solar system looks like with some internal details. Energy space model is more or less the same as for anything else. You just have to discover that if you look at this solar PV control, there is energy stored here and stored in this filter. That's stored energy, then you write your dynamics of the interface. And then you can design power electronic switch control for the battery so that you ensure that power output, real and reactive power, rate of change of real and reactive power, actually is something that you could do subject to your constraints. This is a big issue because we do in markets, we say, you tell me how much power you can produce, you generator, but you're actually not controlling power. You're controlling frequency, your set points of frequency and voltage. So there is no guarantee. And there are all these slips depending on over which time scale you are participating in ancillary or not. Here you control, you design a lot of, and we are spending, with another student who is just finishing his thesis on basically designing nonlinear control for this switching so that in closed loop you can guarantee that solar produces power in certain range at certain rate. We cannot align markets unless we actually have that guarantee. And so there has been a real disconnect between how we control our components for quality of service, for frequency and voltage, versus what we are telling the market, right? So if you think about feed forward versus feedback that John was talking about, feed forward always says we schedule power in the market, right? But am I going to implement it in secondary and primary control? No. Because I have these very nonlinear plans, and I have, for large ranges of changes, I'm not guaranteeing to deliver what I'm selling. So it's worthwhile probably thinking about what are the implications on the market. The other thing that simplifies the thing very big way, now I can have the sort of generalized Drup characteristics for any type of technology as long as my primary control is designed right. So I have incremental power at some rate plus incremental power sent out plus what comes out of the battery, and this is something that gets distributed. anticipated, that gives you what we call distributed energy resource energy conversion relations, which says here is the relationship between the increment in power that I can produce and some comfort that I can tolerate internally. This becomes generalized group characteristic, is not just for generator, but it is not valid unless I do this internal control right. And so in the ARPA-E project, we've done this control for different VRs, for water heaters, and for electric vehicles, and it's being deployed now, I think, the same as with Joanna's program in nodes is being deployed at Pecan Street in Austin. And it's so rewarding not to have to know about all of those details, right? And I'm done. Okay. So this I can go a little bit more over just the math of it, but just for completeness to put it for the market. You're basically exchanging the source, the bidders are giving the bounds within which they can produce something, these bounds, and then the market clears according to that linear optimization problem within those bounds, and so it goes over time, over different time scales. So, done. We did this for with NIST on transactive energy management. You get quite a few interesting things, but that's basically my conclusion. Thank you.
So questions, please. Any questions at the end of the hard day? I suppose. Any questions? Yes, please.
So when you look at these component level, these diamonds, does it matter that these things are vastly different sizes in terms of your interaction model? Do you take that into consideration somehow, or does that affect your solution?
I think this is a really great question, because you can do it without worrying about that, but you know, the aggregation is very interesting. You know, how many of these small ones I'm going to put in one, that's more of a question of organizational. It will work if you exchange information, but if you remember, we had below substation, you have a lot of small guys. So in transactive energy management, they're talking about aggregating at the substation level and going up. The aggregation question, and somebody was talking about it today, is quite open, you know, because it buys you simplifications in terms of what do you need to manage at the interaction level. Yeah. Does that make sense? Okay. Yes?
Yeah, John.
So I'm trying to get a handle on the motivation for the modeling framework. So is it that the motivation is to push the computational complexity to the lower layers, and then you sort of go backwards from that idea?
Well, let me put it this way. With any other research, it didn't happen that way. You know, I don't want to talk about the history, how it happened, but at the end of the day, stop and look and say, it's really helping you with that. But also, we have so many of these complex technologies that if you don't give the guy the freedom to control himself, right? In particular, on the fast time scale, he can tell you that it can do something, but it really can't do. Joanna was talking about demand, cannot do it. I have a completely opposite opinion here, that these DRs, you know, they should be able to control, and they should not commit more, because they can have the trade-off with their control between not knowing what the temperature would be versus their comfort and so forth. So you have full control. So that's one thing. And the other one is just this, you know, getting lost in numbers, in complexity, right? I don't know how many people have worked with transient stability analysis. I know Louis has worked for many years with Hydro-Quebec and so forth. You have these numbers in, numbers out. It's very hard to interpret cause and effect, right? And so, and the other thing is that the market signals are really, right now, in terms of power and energy. So if we just extend it to this rate of change, and we can negotiate, is it rate of change of real power and Q, or just one or the other, it has a little bit implications, then you actually can sell something that you can guarantee that you can control, and it has a value, well-defined value. And this caught us by surprise that in energy space the coordination is linear optimization problem. So that is a big deal. I hope there are no errors, but would be very interested in feedback. Yeah.
David. Marija, it's fascinating to see the connection back to dissipativity.
Yes.
My subject before power system. So the big question we had years ago was developing Lyapunov functions for stability analysis, and in dissipativity theory there's this nice scaling aspect that like all passive systems together are still passive.
Yes, additivity.
Contractive systems, which Jean-Jacques made a lot of use of, contractive systems put together are still the whole thing is contractive. But we never had really good Lyapunov functions for voltage behavior. That was always difficult.
Yes.
Much more difficult than for angle behavior. So is there some prospect of...
That's exactly, I don't want to go now to the slide, but that's exactly what I showed, because supply function is Q dot. That's voltage.
Can you scale it up and get a Lyapunov function across a big...
It's the sum of all of the, like the Lyapunov function is sum of those integrals of 4et, and that's actually the work in tangent space.
Okay.
And I think
Published?
yes, it's published. Yes, it's published. I think I sort of put most of the references there, but I'll be happy to share. Yeah, because that's why I mentioned, because my students use your and Moylan paper all the time, because I think what happens there is that exactly what you said. You could not define the Lyapunov function and supply function well if you have the voltage dynamics. And this came somehow through some other developments, and
there was always some hope. I remember Chris DeMarco years ago presenting a kind of an energy framework which had promise.
Right.
Something, I don't know, never got finished.
the problem is a lot of those, and some people are working Hamiltonian systems, the problem is that those conditions get so messy mathematically. Here is, I know physically that I can take any combination. If I don't push more at a faster rate power in, then it dissipates. It just makes physical sense to me, and then I can have different combinations if I design my components. So
Shows you we shouldn't retire, because these old things come back and may be better.
okay, thank you.
You have good memory, so that's a problem. To remember what's
I just wish I were like 20 years younger, so I can actually work on this. So that's why I wanted to share with people. Yeah. Okay. Thank you.
And any other questions, please, from the audience? Yes, please.
Yes.
I was curious, maybe I just missed something. When you have this dissipativity-based condition for global stability, does this also guarantee the stability of the local state space model, or is that assumed by the local?
That's an excellent question. I forgot to mention about this. So as long as, okay, so the entire state, original physical state on the component, you can break into something that we call X bar, which is internal state, which is not directly affected by interactions, and these Z interaction variables. So the remaining internal states, which can be many, many, they have to be controllable and observable internally. Yeah. So that is the condition. And so you design this physical control inside. The Xia Miao is finishing his PhD thesis on, it's really, that's also spooky that you can have similar concept for these local control designs for inverter-based control, solar, as for synchronous machine. The same form of equations. And that is, he pointed out that is you design this local control so that internal states are stabilizable, right?
Okay, thank you. Any more questions, please?
Okay.
Yeah, if there are no more questions, then thank you very much,
Thank you.
Marija.